So when you're making stuff like games or something, you need to have, or you need to track multiple entities as time goes by, or have those entities change. So that introduces a lot of problems, such as allocating things, the communication between things, keeping the time so everybody goes at the same pace, and as well as the allocation, making sure there's no memory leaking. So I tried and came up with an alternative to multitasking. Is not quite multitasking, because you are not changing the context, or you're not switching registers, or making a window of memory. It's just the same program, but it's jumping around as if you would call uh, a program normally. However, this has um, the tasks have memory allocated to them, and as you go jumping around, they all act as if they were separate processes. So you have 64 bytes or 16 words of user memory, and then this memory is split in the active word, which says if the task is active, two words for the timer, the previous time and the difference, the delta time, and as well as the address of what will you call when you enter this task. After that, you have 12 words of user storage, and this makes it really easy to make the spawning of other tasks. You can do precise waiting, although I'm using milliseconds, but the timer resolution is microseconds. You can use to make incremental movement as like you would in games, as well as state machines. So now I want to show you a little implementation. This is a little bit larger than what I have, because I am commenting it all around. So we first start with the red word here, Tmax, which has 127 total tasks allocated. Then we start allocating the memory for those tasks, and you just multiply it by 64, that 127, and then you zero those tasks using this number fill routine I have here. Then to access the current task, you make a new word, call it ctask, and ctask at the first word that word has is a number. That means here in PC32 I can use it as a variable. So I can make ctask change itself, or another word can change this one here, incrementing the ctask number. Now, okay, you want a new task. So you get the maximum task, and you start a loop to see which task is free. So the task that doesn't have the the first word in the memory space doesn't have a 1, or it has a negative number. So if that task is 0, you drop the loop and you subtract the maximum task number, and you get an address of the task. So if the loop completes, that means there's no task available, and you say tasks full as a string, and you jump into the error routine, so that will stop compilation at that moment. Then now, how do we access the user storage? Right, so the user storage is, we have the ctask word that will give you the current task you are in. So if you are in whatever task you made, you can always call that word, and it will say, oh, you're this task. Okay, so I know which task I am, then the rest is just getting the memory. So I have the word here, tdata, which just shifts the number of the slot I want, and adds it to the current task, and td add, which you'll just read the data. Now the next most important part will be the timing. So we have PMS, which will give you the delta time of that task. So how long has this task been running? You can also change the delta time. So for example, the task executes something and you want the task to execute it again after a certain amount of time. You go ahead and you zero your delta time, and that's how you get timing loops. Okay, so next is the most important word, I think, is the yield word, which will increase the C task here. So you can see one C task as a reference, and U plus star V, which will increase the number, this one here, it will be increased. So you increase the current task and you check if it's valid. So if it's valid, you increase the delta time, and you fetch the function and you jump to that function as if to call the task. If the task is not valid, then you just go ahead and jump to yield once more, and just keep repeating, keep iterating the tasks. Finally, after you're done with the task, you can call inside the word that calls inside the task itself, you can call tdone, and that will zero out the first user storage of the task, and that will simply skip it and mark it as a free task to fill with another one if you spawn one again. Okay, so finally you need to create the actual tasks. So first we have up here in task, you will call end task, so new task here, and it will fall through to the next word. We will just be task store, which you will be storing the task, the time, and you will also be storing four user variables, just to have something to kick off the task at hand. You can also do the plus task, and you can also do for task, which will oh sorry, here in task store, it will store the just initialize the task. Here in for task, it will actually store the user variables, the first or the second four user variables you want to use. And finally, here is twait, which is I think the most important part. Here you will get the timing, and if the timing is less, you will simply yield. If the timing is greater, you will drop the function call, so you don't start wasting timing. No, you don't start wasting um, return stack slots. So you will drop that call and you will just yield once again. So finally, you have the usage of the tasks. So tasks are coded as normal definitions with the word yield compiled as a jump. So you compile it as a in the golden color or yellow. If I don't know if you can distinguish the two colors. So in order to start the tasking, you just have to call a word that has yield inside it and that has been added to the task pile or task stack. So now here we have a little example. It's called a horse race. And here, up here in this comment here, I have slot number 4 as X, slot number 5 as Y position, slot number 6 as character, although this time I'm printing a string. I forgot to change that. Slot number 7 will be the rate of advance of the horse. And slot number 8 will be the wait time. So down here, we have 3 horses, Honey, Bagel, and Lester the horse. And each horse has, if we read it in the reverse, the comment in the reverse, you have an X position, a Y position, the character, or in this time, the name, and the 7R, which will be the rate. So I'm calling for task to include those four parameters as a task initialization, and the task itself, which will be used for all three horses, is this t.horse, which you can up here see. You fetch the x, you fetch the y, you convert them both to integer values, so IV. That's just because these numbers down here, these are fixed point values. So in order to put them on the screen, you need to convert them back to integers. And you set the position of the raster on the screen. Then after you set the position of the raster, you print the string, and if you have to wait, you wait using the t wait here, as you can see. Then you increase the y position using a random number. Again, the random number is a fixed point. Um, I ended with 123, so it's in the range of 0 to 1.0 positive. And you add that to the position y, multiplied by the rate, which is at the slot number 7. So now here, Lester the horse has he's a very slow horse, so he has some time getting started. So I want Lester to wait 650 milliseconds before starting to run. But in exchange, Lester will run at 1.2 point the speed of the other horses, which run at 1.0. So that's the base speed. They all start in the same position y at 80, and they all spaced around. Okay, so I call for task, and for task leaves you the task on the stack. So I add, I want to set the 8th position of the user storage. So I get 8, shifted, multiplied by 4, added to that, and finally store the waiting time. So I have other tasks here. The task that sets the frame, which is just checks if we have to exit the program, clears the screen, sets the color, and then yields. And finally, the tasks that will display the screen. It will display the winning line here in color number 6, which is the blue color of the blue words here. And then you will display a rectangle and finally display and then yield. So as I said before, if you call t.frame, that will kickstart the example. So let me press F5, and you can see that Lester waits for a second and starts running, and let's see who wins. And you can see that Bagel the horse won. So if I press escape and run it once again, let's see if Lester wins this time. And it seems it doesn't want to win, and it still doesn't win. So that's it pretty much for my presentation. Lester didn't win, but he won a lot when I was writing this. So thank you for watching. My site is dscf.co.uk, and you can check my YouTube at New Tech Studio 9236. I make tutorials every now and then. I'm trying to document how to make things in PC32. So thank you very much.
Thank you very much. Has anybody got any questions?
Let me unshare. Stop share. Okay.
Julian, I have a question. You can add a task when the program is running?
Yeah, sure. That's the whole point. You can free tasks, and the task itself can spawn other tasks. So the tasks, they can, let's say, you wanted to have like an explosion, and the explosion will create bits of
Okay.
rubble or something. They can be spawned. And if you want some interactivity, you can make the command line a task itself. So while the yield loop is running, you can add other tasks using the command line.
Okay. You have a unique array of tasks, and
Yes.
you can put the task, and always the computer traverse this array and execute when need.
Yes, yes, and unless you fill the task space completely, this is pretty rock solid. And I think it's pretty easy to implement even in other ports. It should be really, really small, like like 12 lines or something, like maybe 20.
What happens when you have an error in a runtime with one task, and it's easy to see or to detect when
The
you
task
have a problem?
Yeah, you can do it. I didn't really do much error management, but if you can, if the task itself can print stuff to the screen,
Okay.
so it's not like a an automatic debugging. You still have to do work, but it's
You
really easy. It's not that complicated.
you log the task, and then you search the error with the login screen. And
Yeah,
I think,
if the task had an error, it could write I couldn't find this to a memory that has the same offset as the task, and you could look that up. I just didn't implement too much error other than, oh, the tasks are full, you can do that. But because I don't really have much error, too many errors pop, so there's that.
okay, thank you.
Thank you.
Anybody else got questions for Julian?
Okay,
Thank you for that fantastic presentation.
thank you.
So, thank you. So,
Yeah, that was terrific. Very interesting to see some colorful stuff.
next